Alright, time for another draftphysics.com video presentation. Debate physics also, where you'll find a playlist, so to speak, of these hopefully short videos on single subjects, essentially refuting the kinetic energy theory. So today we'll talk about friction and rolling things, and this isn't really a cited experiment directly, but it's indirectly cited when you ask physics to show you it taking 4 times the fuel to go twice as fast. They'll often talk about braking distance or rolling distance instead of just showing you what they should be showing you, and they can't because it doesn't happen actually. Alright, so this is basically the same as the gravitational argument. You could just drop these things instead of roll them, and you're basically just saying you're going to use friction to take the energy out. So the thing has some kind of energy, whether it's momentum or kinetic energy, it doesn't matter. It has a mass and a velocity. Whether you square things and halve things isn't going to change anything. It's a mass and a velocity, and you propel it. So this has twice as much of that. Okay. And in terms of it has twice as much velocity as we're using the same mass. Okay, and you want to roll them on a surface. Fact is, the one that goes twice as fast will actually go 4 or even 5 sometimes the distance. Okay, it'll roll much further. Okay, than twice the velocity. Now, to some, platypus duck kind of comparison, you could say, "Oh, that seems like it sure looks like 4 times the energy. Look, it went 4 times as far." Well, it doesn't really need 4 times the energy to do that because of the advantages velocity creates. So in this circumstance, you're using gravity to apply your friction. Okay, you're taking the energy out using a gravitational process. And the gravity does in fact have rules about velocity. The faster you go through gravity, the less it's going to affect you. It's a time-dependent force. And the fact is that this rolling distance and this rolling distance will have a 2-to-1 relationship. This will only take 2 units of time. So even though it's 4 units of distance, it'll only take 2 units of time. This is only 1 unit of time. And effectively, just like in gravity, this part of the voyage, this velocity, will be exactly the same as this one here. You'll reach half your speed here. 3/4 of the way down the track is where you'll end up going half the speed. And that's the real giveaway that this isn't linear. That is, the amount of friction, okay, the amount that is being taken by the ground, the amount of energy the ground is taking from you. You are consuming the energy. We're applying a force against something. We're allowing there to be an electrical contact, is how you could understand it. We're allowing contact, and we're going to pull the amperage or the wattage out of something because we've improved the contact. And the faster you go, the less contact you have with the surface. So you're losing less per foot, and then you lose more the slower you're going. Now obviously this is a very nice linear curved line, and I'm not drawing it as a curved line because your velocity is decreasing based on a curve, and then this velocity is based on a curve, but the two curves are different. This curve is more dramatic than this curve. You're losing more energy here than you lost in this whole section here. So this whole section, this whole unit of time, you lost the same amount of watts. Okay, if we're going to turn it into something else to understand it, you pulled the same wattage out of the rolling object here that you pull out here because there's more friction here. There's more weight on the ground because you're moving slower per foot, so that means you're losing less per foot over this distance. So it's simply just back to Galilean 500-year-old physics that can be understood, that there's rules to everything, and the rules to losing your energy to something means if you have to make sure it's linear before you claim it's linear, and this isn't linear. That is, it changes dramatically as you go slower and slower. More and more energy is pulled out. So I could draw these lines a little more accurately by you start off, the faster you're going, the less you're losing. The slower you start going, the more you start to lose, until you finally get to the end where per inch or per foot you're losing a lot of energy per foot. But by time, it's all the same. This is the same as this. two units of time. Okay, so just frankly just saying to you that this is a time-dependent force. It only takes twice the time. There's only twice the energy that you're pulling out by gravity. And again, the fact that it's half the speed here instead of here in the middle is what demonstrates that it's doing the same thing that gravity does. So you have to use some other kind of friction that isn't gravity dependent if you want to fairly or evenly consume something's energy. You have to apply some other force that isn't time dependent, some force that is in fact incident dependent, or it just depends. It's going to do the same thing each time, like bowling pins or some other thing. Bowling pins aren't perfect because they stand up in gravity, but anyway, some other mechanism to pull the energy out where it isn't dependent on that mechanism changing as you change the amount of time. Alright, so it's really not an argument for the kinetic energy theory. The fact that it rolls 4 times this far means nothing in terms of figuring out how much energy you pulled out, because you pulled it out differently depending on how fast it was moving. It's as simple as this scale, and you could just logically understand the faster you go across the scale, the less you're going to weigh. And the slower you go, the more likely it is you will weigh your full weight. So as soon as you go fast enough, okay, where you're going to weigh something less than your actual weight, it'll get less and less the faster you go. Alright, that should do it. So it won't be a refuted argument. Nobody will say anything to debunk it or refute. That's how it does work.